In this segment, we will discuss a very important class of molecules. These are the so-called organic molecules. These are the molecules that compose most of living nature. For instance, the molecules that make up plants or our own bodies. Now let's look at this set of deliciously looking fruits and vegetables. One of the components of fruits and vegetables is this molecule, or this molecule. They are the same actually, represented in different ways. This is vitamin C. Vitamin C is an organic molecule. It's organic because it contains carbon atoms. In fact, organic molecules are compounds that contain carbon. But in addition to carbon, they contain often more elements. Let us look at a couple of more organic molecules. This molecule is the octane molecule. Octane contains 8 carbon atoms. Octane actually is a so-called alkane, a particular type of organic molecule. In addition to the carbons, it contains hydrogen atoms. Octane is an important ingredient of gasoline. The next example is an active component of aspirin tablets. It is a much more complex looking molecule, yet it contains carbon atoms. In addition, it contains hydrogen atoms, and it contains oxygen atoms. So in organic molecules generally, besides carbon, we have hydrogen atoms, typically oxygen atoms. It can also contain nitrogen atoms, and it can contain halides, which are fluorine, chlorine, bromine, and iodine. In analyzing and understanding the structures of organic molecules, it is helpful to look at a couple of common bonding patterns. Here's the bonding pattern of hydrogen atoms in organic molecules. They always have one covalent bond, indicated here by the line. So each hydrogen atom is connected with one covalent bond to its neighbors. Carbon, on the other hand, has 4 bonds. Now these 4 bonds can be 4 single bonds, or 1 double bond and 2 single bonds, or 1 triple bond and 1 single bond. In each of these cases, there are 4 bonds. Nitrogen is another important ingredient of many organic molecules. Unlike carbon, which has 4 bonds, nitrogen likes to have 3 bonds. Now these 3 bonds can, once again, be 3 single bonds, or 1 double bond and 1 single bond, or 1 triple bond. In addition to these covalent bonds, nitrogen has 2 electrons that do not participate in the formation of a covalent bond. These 2 electrons are called a lone pair, and each nitrogen atom has a lone pair on it. We typically indicate this lone pair by 2 dots to indicate the 2 electrons. Oxygen, another important element in organic molecules, likes to have 2 bonds. These 2 bonds can be 2 single bonds, or 1 double bond. Now, similar to nitrogen, oxygen also has lone pairs, electrons that do not form covalent bonds. Oxygen has 2 lone pairs, indicated by 4 dots on the oxygen atom. Finally, let's look at halides. Halides, like fluorine, for instance. They are bonded with 1 covalent bond to their neighbors in this structure. In addition to this 1 covalent bond, they have a total of 3 lone pairs that we indicate here by those 6 dots. These are common bonding patterns that are so important in analyzing your structures that it's really helpful to memorize these bonding patterns. Here is an organic molecule. This is C3H4. It is a compound that contains 3 carbon atoms and 4 hydrogen atoms. We can draw this structure, for instance, like this. In this case, the first carbon atom all the way to the left has 2 connections to hydrogens and 1 connection to a carbon atom. The next carbon atom is only bonded with carbon to its left and to its right. And the last carbon all the way to the right has again 2 connections to a hydrogen atom. However, this is not the only structure with the chemical formula C3H4. For instance, the second structure here is also C3H4. It has 4 hydrogen atoms and 3 carbon atoms. The structure, however, is completely different. Here, the first carbon atom, all the way to the left, has 3 hydrogen atoms attached to it. The second carbon atom has two carbon atoms, one to the left, one to the right, and the last carbon atom all the way to the right has only one connection to a hydrogen. So how do we discriminate between these two structures? They both have the same chemical formula. Well, in order to do this, we typically write these structures in terms of their condensed structural formula. In condensed structural formulas, we specify for each carbon individually to which other elements they are bonded. In the first example, the condensed structural formula is CH2, C, CH2. Why is that? We write the structure from left to right. The first carbon atom all the way to the left is connected to two hydrogens. So this is the CH2 unit. The second carbon is connected only to carbon. That is just a single C. The third carbon is connected once again to two hydrogens. So this is another CH2 unit. So the structure is written as CH2, C, CH2. The second example is written as follows. It starts with a CH3 unit all the way to the left, CH3, then followed by a single C, and then all the way to the right, a carbon connected to a single H, which is CH. So from left to right, we read CH3, C, CH. Now note that each carbon in these structures is connected with 4 bonds to its neighbors. Each carbon has 4 bonds. These bonds do not have to be single bonds. They can be double bonds or triple bonds. But each carbon must have 4. Based on this rule alone, we can specify where in the structure there needs to be a double bond or a triple bond. In a second structure, for instance, the triple bond needs to be between the second and the third carbon atom and cannot be between the first and the second carbon atom. Why not? Because the first carbon atom is connected to 3 hydrogen atoms, which is 3 bonds already. It can only have 1 bond more. The triple bond, therefore, must be to the right of the second atom. Let's try to draw the following condensed structural formulas. The first structural formula is drawn as follows. All the way to the left, we see a CH3 unit, followed by a CH unit. The CH unit has 3 neighbors. It has 1 hydrogen neighbor and 2 carbon neighbors, a total of 3 bonds. However, it must have 4 bonds. That means this CH unit must contain a double bond. A double bond in this case must be to the right, because to the left there's a carbon atom that already has 4 bonds. It cannot accommodate another one. Then another CH unit, followed by, all the way to the right, a CH3 unit. The second structure is drawn as follows. It contains, from the left to the right, a CH3 unit, followed by a CHO unit. Now the CHO unit contains 1 hydrogen and 1 oxygen bonded to the carbon, in addition to a link to its neighboring carbon atom. That is, again, 3 neighbors, which means one of the bonds must be a double bond. This double bond is between the carbon and the oxygen. That's the only possibility, because hydrogen can only have 1 covalent linkage, and the carbon to the left already has 4 bonds. The only possibility for a double bond is between the carbon and the oxygen. Now, remember that this pattern, a double bonded oxygen, is a common pattern we just discussed. Let's look at 2 more examples and try to draw these structures from their condensed structural formulas. The first structure is drawn as follows. From the left to the right, we see a CH3 unit, followed by a CO unit. The CO unit includes a carbon atom connected to 1 oxygen. The carbon atom is also connected to 2 carbon neighbors. That's a total of 3 neighbors. It must have 4 bonds. So there's a double bond. And a double bond in this case must be between carbon and oxygen. The last unit is again a CH3 unit. The second structure is drawn in this way. It starts from the left to the right with a CH3 followed by a CH2 unit. And the CH2 unit is drawn in this fashion. It has 4 single bonds, 2 to hydrogen and 2 to the carbon left and right. Then we see a single oxygen. A single oxygen sandwiched between two carbons is drawn in the following way. Two single bonds and two lone pairs on the oxygen. Then again, a CH2 unit, and finally a structure has all the way to the right a CH3 unit.